Hi everybody, welcome to another video in discrete math section 2.3 functions. So a function is defined as an assignment for each element in A. So we have a function from A to B. So a function is assignment each element of A to exactly one element in B. We write f of A equal to B, and B is unique element of B assigned by the function f to an element A of A. And sometimes functions are called mappings or transformation. Of course, this is not the first time we see it, the function, first time we define a function. So now we have more technical terms for a function. And we say f maps A to B. So this is from A to B. Or we say f is a mapping from A to B. It's just some terminology here. A is called the domain and B is called the codomain. Right. Then you say why it's not range. Well, we'll get to that in a minute. Right. If f of A equal to B, then B is called the image and A is called the pre-image of B. The range. Now we got into the range. The range is the set of all the image of A under F. So the range is only the one that are image, the set of all the image. The image is something that has the pre-image. Okay, we'll get to that in a minute. And the range are denoted by f of A. Two functions are equal when they have the same domain, same codomain. Map each element of the domain to the same element in the codomain. Right. So let's look at the first example. Let f be z to z. Assign the square of an integer to this another integer. Determine a function, domain, codomain, and range of f. Right. Usually, the way we define a function for Cauchy algebra, trigonometry, calculus, or those classes, we define that from the real numbers. But this is discrete math, so that's why we use z. So it's not continuous, so to speak. Anyway, so we have a square. So the square function, so we can just say f, because from z to z. So that f of x equal to x squared. So we make a square, right? Now, determine the function. Well, this is the function. Domain, of course, that's z. Which is the set of integers. And then the codomain, of course, that also z. And set of integers. But what will be the range? Remember, we have the square. 1 square is 1, negative 1 square is, let's look at some values. F of negative 1 is negative 1 square, which is 1. F of 1 is also 1. 2. So we don't have, if we want 3, we don't have square root of 3 because we're not dealing with irrational number. So it has to be, so the range in this case is the set upon the perfect square. So we'll go from 0, 1, 4, 9, 16, and so on. So the range is different than the codomain in that sense. Right. Next, we define injection, projection, and bijection. One-to-one or injective function is called injection. If and only if f of A equal f of B implies A equal to B for all A and B in the domain of f. So first of all, we know that for a function, each one in the domain can only have one arrow. So we cannot have A that give out that shoot 2 arrows. That would not work. X would not be a function. So we know A only, each element here only shoot 1 arrow. But the 1-to-1 meaning that each of them shoot 1 arrow, and the arrow have to go to different target. They cannot shoot at the same target. Let's see if there's A and there's B. If both of them shoot into the same target, let's see Z. In that case, if f of A equal f of B, then A have to be equal to B. This is different. A and B are different. They cannot shoot on the same target. So injection cannot be that. Injection 1-to-1. So each one of them shoot at a different target. I just want to write each shoot like shooting an arrow, different target. Alright, next we define onto. Or trajective, we call the projection. Now, this said, if and only if every element B in B, there is an element A with f of A equal to B, meaning that every element is a pre-image. Every element is an image. So element in B has a pre-image. There exists an A, so that has a pre-image. And function is 1-to-1, and meaning 1-to-1 corresponding or projection if it's both 1-to-1 and onto. So if we have both of them, both of this, they call the projection. Okay. We will see some example later. Now the method. Now this will tell us to show that if f is injective, we show that if f of x equal f of y, then x and y belong to A, and then x equal to y, meaning that if the targets are the same, those 2 arrows have to come from the same origin. So if there are 2 arrows come to the same point, we cannot have that. If 2 arrows come to the same point, they have to start from the same point. That's what essentially an injective means. If we want to show that it is not injective, very easy. We just find a counter example. Just find a target where there are 2 arrows shooting at it. So that is not an injective. Now, to show that it is projective, we just show that every element has a pre-image. And because if we want to say this is not projective, we just find one that does not have a pre-image. Alright, look at some example here. Let's f be the function defined like this. Well, we're just going to demonstrate by just do the illustration. Just draw it. A, B, C, D. And now we have 1, 2, 3. Okay. F of A equal to 3. F of B equal to 2. F of C equal to 1. And f of D equal to 3. Right. So when we look at this map, we say that every member on the second set, every member in the codomain has a pre-image. So this is a range also. So each one of them has a pre-image. So that means it is on 2. Each has pre-image. Each in the second set, let's call this second set B, has pre-image. Now, is it 1 to 1? Well, if we look and we see that number 3 here, they have 2 arrows going to 3 and 2 different arrows, one from A, one from D. So this is not 1 to 1. Because we have f of A equal to 3 equal to f of D. So 2 different arrows come to 2 different places, go to the same target. So it's not 1 to 1. Right. Next, we have f of x equal x squared from the set of positive real numbers to R. Is that on 2? Is it 1 to 1? So if it is on 2, then every one in the second set has to have the pre-image. I'm just going to say it. How about if we look at, let's say we have one from f of x equal to x squared. Let's say we make a table. Right. Let's say if we have 2 for x squared, then before that we have to have square root of 2. That's perfectly fine, right? So square root of 2 gives us 2. That's fine. However, if we have negative 1, there's no real number that gives us negative 1. It would have been imaginary. I squared is equal to negative 1. But of course, I does not belong to this set. So, we have the set, we have an element in the second set that does not have pre-image. So negative 1 has no pre-image. So that's why this is not on 2. Negative 1 has no pre-image. Right. Or we say that there doesn't exist an x in this set such that f of x equal to negative 1. So we have negative 1 in the second set, but there's no x in the first set that satisfies this. Or we say no pre-image. So it's not it's not on 2. Is it 1 to 1 though? To show that it's 1 to 1, we have to use this. So the thing is, this is from positive, so that makes everything different. So let's say if we have f of x equal to x squared, and then we have another y is also equal to x squared. Actually, this is a terrible way to denote that, so let's not try that. So we have x squared equal to y. Of course, if we want to solve for y, y can be equal to plus or minus square root of x. Now, this time, so x is in R plus and y is in R. Now, notice that x in R plus, so we cannot have the negative, right? So there's only one square root of x. So we don't have the negative square root of x because that would be negative. So in that case, we only have x in that. Of course, the formal proof is a lot more than this. But suffice to say that because we only have positive numbers. So each one of the positive numbers here will give out 1. Okay, think about this. If we have negative square root of 2, give to 2. This would not be a 1 to 1 because square root of 2 gives us 2, negative square of 2 gives us 2. This would not be 1 to 1. But we restrict the domain to be only positive numbers. Then we don't have this negative case. So it will be 1 to 1. It is 1 to 1. Right, now inverse function. Right, let f be a 1 to 1 corresponding from A to B. The inverse function of f assign each element from B to the unit element in A of A. So pretty much, if a function from A to B, then the inverse from B back to A. That's called the inverse function. And we denote the inverse by the -1. And we never say f to -1, we just say f inverse. So f inverse of B is equal to A when f of A equal to B. So from A to B, then from B to A. Just draw this quickly. A function give us A to B, and the inverse give us back from B to A. Right, now let f be from G to Z determined by that. Is f invertible? If so, what is the inverse? Well, it's easy. So instead of go from A to B, we go from B to A. So let's say we have y, replace that by y. And now from A to B, from B to B, A, so we switch in the rows. So we're just going to switch in the x and y. And now we just solve for y. X minus 1. So we said the inverse is going to be equal to x minus 1. Right, so to find the inverse, this is the step to find the inverse. Of course, we'll see that. In course algebra, trigonometry, pre-calculus, even calculus. But of course, we'll review that in a bit. Right, bottom line, to find inverse, these are the two steps. Next, suppose we have the square function. Is it invertible? If so, what is the inverse? And the answer to that is this is not a one-to-one function. Remember, we have to define this have to be one-to-one to be inverse. And we say that this is not, in general, if we have the R plus, then it is one-to-one. So for R to R, this is not one-to-one. So not invertible, meaning there's no inverse. Now think about that. We have f of -1 is equal to 1, and f of 1 is also equal to 1. Now think about that. If we have -1 and 1, both of them shoot at the same target of 1. So that is a function going that way. There's nothing wrong with that. Now if we go for the inverse, we don't know should the 1 go back to 1 or the 1 go to -1. So one side is okay, but when we go back, we don't know which one. We have to return the arrow to. So in that case, it's not one-to-one, therefore it's not invertible. Right. Now, note, I leave it blank here, so we write a few things here. So first, in terms of the domain and range, the function and inverse are flip-flop. So we say domain of f is equal to the range of the inverse. The range of the function equal to the domain of the inverse. So the domain and range are interchanged. So that's the first step, the first thing. 2. And to find the inverse of f of x. This is in course algebra. There are 4 steps. Number 1, let's say the function equal, replace y into f of x. Second step, this is for the inverse, interchange x and y. and then we solve for y. And finally, just use the proper notation. We'll replace the proper notation back into y. That's how we find the inverse. By the way, this is not defined in the book in discrete math, but in coarse algebra, trigonometry, pretty much all the previous math, we define the inverse. If f of f inverse equal to x, and f inverse of f of x equal to x. So this is a definition of the inverse function. Right, so we have these properties, and that is how we find the inverse. And another characteristic of inverse function in terms of graph is that the function and the inverse, the graph of the function and the inverse are reflection on each other on the line y equal to x. I should say the graph of y equal f of x and y equal to inverse are symmetric on the line y equal to x. So those are the three things. Right, next, find the inverse for the function f of x equal to x squared for x less than or equal to 0. Notice that if we don't have that condition, then that could not be a one-to-one function. Therefore, there will no inverse. So we add that condition to guarantee that it will be inverse. We'll look at that in a little bit. Right, so how do we find the inverse? Well, those are the steps. So first I'll replace f of x, replace y into that. So y equal to x squared right? Now we interchange x and y. So y become x, x become y. And then next, solve for y. So if we have y squared equal to x, or x equal to y squared, same thing. If we want to solve for y, we have to take the square root on both sides, which gives us plus or minus square root of x. Now that is a big problem. In general, if we have an x give us a square root of x and an x give us negative square of x, this is not a function. So this doesn't work. So that's why we have to do something here. Right? So what's that something? Now, notice that we do have the condition of x less than or equal to 0. So when we interchange x and y, remember we have to do that as well. Here from x less than or equal to 0 now turn into y less than or equal to 0. When we interchange x and y, right? Now if y is less than or equal to 0, we can only choose negative. Can only choose that. Choose negative because y is less than or equal to 0. So in that case we have y is equal to negative square root of x. And we use the proper inverse notation. There. Now, let's look at the graph. So first, we have x squared. So in general, x squared parabola look like this. But of course we only have the part that is positive, so we only choose this part. Of course the one-to-one function, the way we define it in terms of graph, is past the horizontal line test. So this branch, not the one on the right. Right, so this is f of x equal to x squared when x less than or equal to 0. Now we're going to graph square root of x. Square root of x is this, and then we'll reflect that because of the negative. Right. So this is f inverse of x equal to negative square root of x. And of course we see that the graph is symmetric on the line y equal to x. So the graph of the function, the inverse, is symmetric on that line. So that's why it works. Right. So once again, this is how we find the inverse, and we can check the graph of the function, the inverse, are symmetric on the line y equal to x. Right. Right. Next, we define the function convolution. Convolution from A to B and then from B to C. So pretty much convolution of f and g denote f of g of x. This is f of g of x, meaning x from A to B and then from B to C. So this is g of A, f g of A, the function g, function f. So that's pretty much the convolution, right? From A to B, from B to C. Right. Now let's f of x be x squared and g of x be 2x plus 1. Find f of g of x. Right. So first we see, by the way, this is equal to f little circle g of x, because we can ask that as well. So f of g of x. F of g of x. First of all, I will ignore what inside of this. We look at the function f, which is just something square. Now, that means whatever inside the x, we have to substitute in the same thing. Here we have g of x, so I'm just going to have g of x square. And g of x is 2x plus 1. So I have 2x plus 1 square. Right, just like that. Now, this is g of f of x. Of course, if we write that, it is equivalent to g little circle f of x, or g of f of x. Once again, we will ignore whatever inside of the parentheses, and we just say the g function is 2 times something plus 1. And that something is f of x. That's what we have. And f of x in this case is x squared. Yeah, so that pretty much how we form an inverse. Now, here's another example. Let g be a function from a, b, c, such that f of a is b and g of b is c and g of c is a. So we go from ABC to ABC. And then let f be a function from ABC to 1, 2, 3. With that, right, what is the combination of f and g? Right, so let's just draw. First, we have the function g. Don't write like that. will get very grounded quickly. Just going to say from this set to this set, that is G. And then from whatever that is, we're going to go with F. So that is the combination of F and G. Meaning F of G or F of G. Right, this is what we asked to find. Right, from function G, from ABC to ABC. So we have F of G of A is equal to B to A, give us B, and B give us C, and C give us back A. And after that, the F give us 1, 2, 3. So we say A, F of A is 3, F of B is 2, and F of C is 1. So when we write the combination F of G, we will write the order pairs this. If we start from A, it will go to B and then to 2. So we have A and 2, like an order pair. And then if we start from B, it will go to C and to 1. So C and 1. And then C go to A to 3. I'm sorry. B to C, then C to 1. So this should be B. And then C to A and A to 3. So C 3. Right. So that is the function. Now what is the combination of G to F? G and F. Meaning we ask to find G of F, like that. So first, so we have to do F first, and then G, right? Remember, it's always inside out. X to function G of X, and then to F. Same thing, G of F of X is equal to G of F of X. Oh, that's right. So F is ABC 1, 2, 3, A to 3, B to 2, and C to 1. And what is G? G is this. Well, we cannot have from 1 to 3. So it doesn't. So we don't have that. Because of that, this one is undefined. Because there's no corresponding between this set to that. Right. Right. Graphing function. Now, let f be a function from a to b. Then the graph of the function is a set of own order pairs a, b, so that a is in a and f of a is equal to b. Now graph f of n equal to 2n plus 1 for the set of integers, the set from integers to integers. So in that case, we just plot some points. Let's say we start with -2. Just pick a random number. 2 times -2 plus 1. So -4 plus 1 is -3. negative 1, that is negative 1, negative 2 plus 1 is negative 1. If we put in 0, put in 1. So remember, this is from integer to integer, so we have the points. We plot them, but we do not connect them. Connect them is could be continuous, could be real numbers. We're not doing that. So negative 2 and negative 3, negative 1 and negative 1, 0 is 1, 1 is 3, and because if we just keep continuing, we have those points. Just isolated points like that. Right. Graph of y equal f of x equal to x squared. Well, this is continuous. So we have the graph. Like that. Right. Next, we define some special function. The floor function is the largest integer less than or equal to x. So if we have the floor of 3.5, it will be 3. The floor of 4.9 is still 4. So we're not rounding up. We round everything down. If it's floor of 4, it's going to be 4. Right? So floor is pretty much round down, if you will. And the ceiling is the smallest integers that greater than or equal to x. So in that case, that is round up. So round down, there's the hook at the bottom here, or the hook on the top is the ceiling function. Right, here's some example. What is the ceiling of 3.5? Well, that is just round to the next integers. That would be 4. And 3.5, the floor of that is going to be 3. Negative 1.5, well, negative 1.5 between negative 1 and negative 2. Negative 2 is smaller, negative 1 is bigger. And this is the ceiling, so we round up. And the floor, we round down. So with that, we have the graph of the ceiling function, the floor function and the ceiling function is that. Right. So the floor is round down and the floor, the ceiling round up. Now say, what if we just want to round that, like if it's more than 0.5, round to the up. If it's less than 0.5, we round down. Can we use the floor and the ceiling function? And the answer is that yes. Now think about this. I'm just going to give you one example. If we have number 3.5 or 3.6, if we round that equal to 4. The floor only give us 3, and the ceiling give us 4. But we cannot teach you the ceiling, right? So here's the trick. When I remember when I took computer science, they said instead of round, we can just say instead of round 3.6 to 4, we can just say round of 3.6 equal to the floor of 3.6 plus 0.5. You plus a half to it. If you plus a half to it, it would be floor of 4.1, which gives us 4. Right? So the round is the floor function when you plus 0.5 to it. Plus 0.5 to it. So if it is 3.2 plus 0.5 to it, it is still 3.7. Round down is still to 3. But when we add 0.4, if we do the floor and if it's more than 3.5, it will do the next one. So the floor is the round is a special case of the floor plus 0.5. Right. Now with that, we have to look at this case. Prove that when x is real numbers, then the floor function of 2x is equal to x plus x floor of x plus the x plus 1/2. Right. Now there are two scenarios. Of course, if we have round of 3.2, then that's good. We don't have to do anything, right? So if we do the floor of 3.2 plus 0.5, that's still 3.7, still 3. So plus 0.3 will be the same. If it's less than 0.5 and more than 0.5, it will be to the next integers when we talk about rounding. Or even floor, if a number. So let's just try. Let I'm just say epsilon be a real number such that it is between 0 and 1. Now consider two scenarios. If n is bigger than 0.5, now let n be a real numbers. In integers. Let n be in integers. Now, an integers meaning the whole number and the negative. So in that case, I should say epsilon. If epsilon is greater than. Now, in that case, any x number can be n plus epsilon. Let any that equal to n plus epsilon. And epsilon is 0.5. Less than or greater than equal to 0.5. Right? And now let's look at the left hand side. Left hand side, the floor function of 2x. Have 2n plus epsilon. So we have 2n plus 2 epsilon. Now, if epsilon is greater than 0.5, I'm just going to, when we write like that, we say if epsilon is from 0.5, greater than 0.5, but still less than 1, multiply by 2. We have 1. Let's write the equal sign here. Could be very difficult to handle. That would be wrong. So just less than. So epsilon is greater than 0.5, meaning from 0.5 to 1, including the 0.5. Now, multiply 2 everywhere, we have this. So this epsilon is only between 1 or 2. So this gives us equal to 2n plus 1, because this is just plus 1 to it. It's between 1 and 2, so it cannot be 2. If it's 2, we have to round up, but it's not. So still just 2n plus 1. So that is the left hand side. On the right hand side, we have x plus 1/2. Now x is just n, and then n plus 1/2 plus epsilon. Now n is whole numbers, integers already, so it will be just n. But this 1/2 plus e is going to be bigger than 1. It cannot be 2, so that's going to be n plus 1. N plus 1 is 2n plus 1. Now the left side and the right side are equal, so it's good. Yeah, let's check. So that is where epsilon is greater than 0.5. Now, if epsilon is less than 0.5, and in that case x can be written as still the same, n plus epsilon. Now let's look at the left hand side. Floor function of 2x. So it's going to be n 2 times n plus epsilon. That would be 2n plus 2 epsilon. Now, let's go back to this. Epsilon now is less than 0.5, but still greater than 0. Let's say epsilon greater than equal to 0, but still less than 0.5. Now multiply everything by 2. You have 0 less than equal to epsilon less than 1. Now if epsilon, 2. If 2 epsilon less than 1, the floor function plus something less than 1, so that's still 2n. And then the right hand side, just n x plus the floor function of x plus 1/2. So it's n plus n plus 1/2, n plus epsilon plus 1/2. Now this is just n because n is on integers. Now epsilon is less than 0.5, so this is going to be less than 1. If it's less than 1, we will not round to the next integer, so just n plus n, which is 2n. Now 2n and 2n are equal, so once again we have the left hand side equal to the right hand side. So it's good. So either case it works, so that is the proof for it. Right. Next we define factorial. So factorial f of n is equal to n exclamation point. So meaning that it is the product of the first n positive integers. So meaning that f of n starting multiply backward to 1. Start from that number going back to 1. And f of 0 is 0 factorial is equal to 1. This is the way we define. This is how we define 0 factorial is equal to 1. So n factorial is equal to n times n minus 1 times n minus 2 all the way back to 1. Right? Of course we can go from 1 to n, but it's better to define from n back to 1. Right. Now, for example, what is 5 factorial? Well, 5 factorial is start from 5, going back to 4, 3, 2, and 1. 5 times 4, 20, and 6, 120 times 6, that's 120. Right. Now, what is 6 factorial? Well, 6 factorial, we start from 6, 5, 4, 3, 2, and 1. That there by definition. But we have to do that. The answer is no. 5 factorial we already calculate. So we can say 6 factorial is 6 times 5 factorial. Because factorial meaning we start from 5 again, go back to 5, 4, 3, 2, 1. Right? So in that case, it's 6 times 120. 720. Now, there's the reason we use that notation. We can also start from 6 and to 5, and if we feel like it, we just stop. The exclamation point, the factorial here, meaning we have 4, 3, 2, 1. So we just stop where we want it. And that particular helpful. For the next one, we can say 10 factorial. That's 10 times 9 times 8, and I feel like I stop here. So we can just cancel the a factorial here. Just have 10 times 9 is 90. So, like I said, our factorial, we start from that number, going back until we hit 1. If we want to stop at any point, just put the exclamation point. That means factorial. We start from that, going back to 1. So that's why we use this notation, particularly helpful. So that's what we have. And with that, we finish section 2.3 in discrete math. As always, thank you for watching, and see you in another video in discrete math.